Okay, here's the follow-up to my last general talk about limiting reactants. This is a specific problem that Liam asked me to do, and it's a combustion problem of propane. So C3H8 plus O2 yields, of course, CO2 and H2O. Now, Liam, in your email, your coefficients didn't make a lot of sense to me, so part of the problem might have been that you didn't balance it correctly. So let's do that first. I'm going to want to put a 3 in front of the CO2 because of the 3 carbons in propane, and because of the 8 hydrogens, I'm going to put a 4 here, so that gives me 10 oxygens on this side. Quickly, I'll put a 5 there, and then I'm done. It's balanced. So the problem asks, if I have 25 grams of propane, and I have 100 grams of oxygen gas, how much, can't remember which product you asked for, Liam, so I'm just going to say water. How much water can I make? All right. So this is a limiting reactant problem. Basically what you have to do is you have to do a standard stoichiometry problem, but you have to do it twice. You have to do it once for the propane, and you have to do it another time for the oxygen. Well, actually, it depends. If you're only trying to determine the limiting reactant, you don't have to do a full mass-to-mass stoichiometry problem, but if you are trying to determine how much product you made, then you do need to do a full mass-to-mass conversion. So I'll show you what I mean. And keep in mind that I'm working without a periodic table, so these are going to be rounded molar masses. Okay, so starting with the propane, I'm going to say that I've got 25 grams of propane. I'm just going to call this A. I'm going to call this B just to simplify things for me. So 25 grams of A, and I want to convert that into moles. So the molar mass of propane, I'm going to say it's 8 hydrogens, so 8 plus 3 times, so 36 plus 8 gives me 44 grams of propane in 1 mole of propane. Now, this is the critical part. In this step, I've got to do the mole-to-mole ratio between component A, reactant A, that I'm talking about, and my product of interest, which in this case is water. So the mole-to-mole ratio is given to me by the coefficients. And there's no coefficient in front of the propane. That means for every 1 mole of propane, I can make 4 moles of water. Okay, that's my mole-to-mole ratio. This is the step that makes it a stoichiometry problem. Okay, this is the stoichiometry part, using the mole-to-mole ratios. Okay. And note that I put 1 mole of A on the bottom so that it can cancel out above. All right. Now you can stop here if you're just trying to determine what the limiting reactant is. But if you want to know exactly how much water you're making, you're probably going to want to go one step further. You're going to want to convert those moles into grams. And so hopefully everybody knows that in 1 mole of water, there are 18 grams of water. Okay, so that's my setup for that part. I'm going to do the exact same procedure for oxygen. Okay, and I'm going to say 100 grams of component B, which is oxygen. Okay, just doing that to save space. And I've got to convert those grams to moles, right? So 2 oxygen atoms in 1 oxygen molecule. That means 32 grams in 1 mole. Okay. Next, I need my stoichiometry step. Okay. So what's the mole-to-mole ratio between component B, which is oxygen, and my product? And that's 5 moles of oxygen for every 4 moles of water. So I've got to put my oxygen in the bottom, 5 moles of B, which is O2, and the 4 moles of water again up top. And that's going to be the same for both of these calculations. Okay, because in both cases you're comparing to the final product, water. And again, the final step will be obviously identical because all you're doing is converting moles of water into grams. Okay. Now I'm going to stop there for a second and have you compare these two calculations. You can see a couple things. First of all, if you look at the amount, you've only got 25 grams of propane and 100 grams of oxygen. But only a novice chemist would say, oh, well then the 25 grams of propane are going to run out. Because that's not what it comes down to. If you look at this, okay, in the propane problem, you're only dividing by 1 mole of propane. That's what its coefficient is. In the oxygen problem, you're going to be dividing by 5. Okay, so that's going to affect what's going on. As a matter of fact, 25 divided by 1, as you can see here, is 25, and 100 divided by 5 is 20. So all of a sudden, this calculation down here is lower. Now, we've got obviously other factors, which are the mass of your separate components, and those are pretty close. So you would have to do the whole thing, and I don't have my calculator out in front of me. You'd have to do the whole thing out to see which is the limiting reactant. But yeah, I don't have my calculator out. So hold on, let me go do that. I'll be right back. Okay, so it turns out the numbers are really close, and I'm going to try to put those in here in purple. This is going to be a little bit messy, but for the top one, all this part right here equals 0.562. And for this one, bottom one, it's this one up here is different. I said that wrong. It's 0.58. And down here, this one is 0.625. So they're really close, but you can see that this, when multiplied by 18, is going to get a number smaller than this when multiplied by 18. Okay, which means this makes less water and this makes more. Okay, that means that this, in fact, is your limiting reactant. So the propane is the limiting reactant. Okay, so the novice chemist would have gotten lucky on that one. The one with the fewer grams does turn out to be the limiting reactant. But as you can see, it did not have to be that way. Okay, because you have to consider the mole-to-mole ratios. I think that's it for this one. I will send it out and see what you guys think. Okay.